This is over specific heat of metal lab, and this is how to determine the C of the metal. So a few notes, and it looks kind of like we got a lot going on here, but I'm going to zoom in over here. So we did a hot water bath in which we got the water going to a boiling point of 100 degrees. And we did the boiling point because generally we know, okay, if it's boiling, it's 100 degrees. We are assuming that all the energy from the water got transferred to the metal. That's why we left it in there for 10 to 15 minutes to make sure we got a guaranteed transfer of energy from the water to the metal. Okay, and that's called a water bath. So that's our Q hot. And our Q cold, which we set up with the calorimeter cup, we had the cup and we had the inside cup where we put 100 milliliters of water in there. And then we measured the temperature of our water. Generally, it was around somewhere around like 20 or 21 degrees Celsius. And that was our cold side of it. And so the idea is that as my Q hot loses its energy, then Q cold is going to gain. And you've seen this before. If you have like the hot packs and it's cold, you run those hot packs up, you put them in your hands, and the energy transfers from your hand from the hot pack to your hands, and your hands feel warmer. So basically, we were trying to do an equilibrium here. And so our equation is Q equals mt delta T. Q is the thermal energy measured in joules. M is the mass. C is specific heat, and delta T is the temperature, change of temperature, or final minus initial, and it's also measured in degrees Celsius. So that's the background for your lab that you did. Okay, so I'm going to take a sample data. This is for the academic kids, and this is how the academic kids will be doing their calculations. So I'll put a mark here. This is academic. There's two sets of calculation we're doing. We're going to calculate for our C, and we're going to calculate our percent error. If you are missing your data and do not have your data, or there's something wrong with your data, or you only got 2 runs, so forth, you are expected to include 3 calculations for zinc in your lab, and everybody's expected to do it. So you may use my data if needed. All right, with that set up, let's do this. So we have set up our equations that the Q hot equals the Q cold. The Q hot is the metal, and the Q cold is the water. And so I went ahead and I rewrote the equation with MC delta T's in there. So I have CM delta TM equals CW delta TW. And now what we're going to do is we're going to go to our table. We're going to start subbing numbers in. And so my mass of my zinc is 22.0. If you prefer to call CM your X, you may do that. That's completely fine. My temperature final is 25.3. My temperature initial was 100 for this run. And that should be negative. And the way that works out is I have a negative and I have a negative on the outside. It ends up being positive because C values are always going to be positive. My mass of water, since water has a density of 1 gram per milliliter, I measured out 100 milliliters of water, so I have 100 grams of water. The specific heat of water is also a known value, which is the 4.18. That number is set. You will always use that number when working with water. And then my delta T, I have my final temperature is 25.3, minus the 24. Okay, now we're going to get this to a number over here. So I'm going to actually break this into 2 steps. So I have negative 22.0 cm, and then the difference of this number is a negative 74.7, and then that equals, and I'm going to go ahead and sum all this up, and when I type this number in, I get 543.4. Now I'm going to simplify this side over here. And a negative times a negative will end up being a positive. So I end up with a positive. And when I do this 22 times 74.7, I get 1643.4. I still have my CM, that's my X that I'm looking for, and equals 543.4. Now we need to solve for X, and so I need to isolate my X, which is the CM. And so I'm going to find out that my CM, when I do this, is kind of a small number, but that's what I kind of actually want. So I get 0.33. And so now what I need to do is I need to do percent error. So my percent error equals, my accepted value for this is 0.38. My experimental value is 0.33. And I'm going to color code these because the only number you're going to have to change is your experimental value. The accepted value will remain the same. And then we're going to get that my percent value for this is 13.23%. And that's how you do your calculations. Honors, we have a little bit more to put into this. So honors, we also are going to look at the fact that it's not just the water exchanging with the metal. The water's in contact with the cup, it's in contact with the stirring rod. And so we're going to add all of that to our calculations. And so I have my Q hot is equal to the Q cold. And on my Q cold side, I've added the water, the cup, and the stirring rod. It's going to be worked the same exact way. I'm going to work with data number 1. And I get 22.0 times, there's my X. I'm already going to push this forward. This is the negative 74.7 because we saw this on the other one as well. This is equal to, so this first one doesn't change. I'm going to go ahead and bump it forward because we saw this in the other half of the video. Now I'm going to put in my mass of my cup, which was 22.12. The C of the cup, and this is going to be set for everyone, is 0.91 because that's aluminum. All right, and then my delta T that I had for that was, it's going to be the same as what we saw, 25.3. 25.3 minus 24. So that's going to stay the same. Whatever the water's is, that is as well. Then the mass of the stirring rod was 10. The C is also going to be 0.91. And then the delta T is still 25.3 minus 24.0. Okay? So I'm going to get this down to a number we saw earlier, 1643.4 times CM equals 543.4 plus, and we'll do the math real quick, of 22.12 times 0.91 times 25.3 minus 24.0 equals 26.16. And then we'll have 10 times 0.91 times the difference at 25.3 minus 24. And it's 11.8. So the one thing I want you to notice is if you watch the other half of the video, we're not getting much change as far as our value goes. But I still want you to note it because it was actually involved in the change. And so we're going to sum these up. So I got 543.4 plus 11.83 plus 26.16. And I get 581.39. Okay. So just as we've done before, we are going to divide out the 1643.4, and we are going to get 1643.4, and we're going to get that our CM equals 0.35. So it may not look like it did much, but for you guys, it should help improve your percent error. And so just as we saw with the other group, we're going to do percent error as well. And so my accepted value, as we saw earlier, is 0.38. So we have 0, whoops, I'm going to change that color. So 0.38 minus 0.35 divided by 0.38 times 100. All right, 0.38 minus 0.35. And this time we're going to get 7.89% error. So for you guys, that should help. All right, so you're going to do that for your zinc. And then honors, you also had your unknown metals. So I will tell you that metals 1 and 2, their accepted value is 0.91 because they were aluminum. And then metal 3 of your unknown was 10, and so that value is 0.227. And so you'll be doing the same thing with your 3 unknowns. You have 6 calculations you're responsible for as an honors, and make sure you include that on your report and turn that in. Have a great day. Live long and prosper.